Alright, welcome to another video. I'm not exactly sure which series I want to do. I guess I was leaning toward wild networking. I'm the most excited about that one. So that's what I'm going to do. It'd be nice if I could get a whole video, or get the RFC read, the whole RFC for BGP, and then kind of reassess what I'm doing with that series and kind of see what I want to do next, because that's, as I've mentioned before, the series that I'm the most excited about. But I think right now what I'm doing, just reading the BGP RFC, is kind of leaves a lot to be desired with it. Other things I could do is read design guides from vendors. So there's like, I'm sure there's like a Juniper design guide. Yep, so we got a solution center here for Juniper. We got a business edge solution. So lots of interesting things here. I could read that. We've got design guides from like Arista. Yep, so here's a design and employment guide. So I think that would be pretty darn valuable. We've got it for EVPN, multi-homing, and data center. Like, I think this is going to be the biggest bang for my buck, because right now I think that's kind of an area I would like to get better in, is just a higher level design architecture kind of view of networking, and kind of get a little bit away from the absolute fine details. But at the same time, it might take me closer to the fine details, because I plan to try to implement it all in the lab. So that's pretty much the key word for me is lab. I just want to be labbing, and what I'm doing now just isn't quite taking me there. So yeah, a actual like design guide, something like that, I think might take me into the lab a little bit more. Oh right, yeah. Here's a one I definitely want to do as well. Yeah. Okay, but for now, if I can read the whole RFC word for word out loud, that's going to be, I think, kind of something I can brag about. And I did completely relearn multi-exit discriminators from reading this, so it has been pretty valuable. So let's continue. This is section 9.1, the decision process. The decision process selects routes for subsequent advertisement by applying the policies in the local policy information base, the PIB, to the routes stored in its ADJ-RIBS-IN. The output of the decision process is the set of routes that will be advertised to peers. These selected routes will be stored in the local speaker's ADJ-RIBS-OUT according to policy. The BGP decision process described here is conceptual and does not have to be implemented precisely as described, as long as the implementations support the described functionality and they exhibit the same externally visible behavior. The selection process is formalized by defining a function that takes the attribute of a given route as an argument and returns either a non-negative integer denoting the degree of preference for the route, or B, a value denoting that this route is ineligible to be installed in the loc/RIB and will be excluded from the next phase of route selection. The function that calculates the degree of preference for a given route shall not use any of the following as its inputs: the existence of other routes, the non-existence of other routes, or the path attributes of other routes. Route selection then consists of individual application of the degree of preference function to each feasible route, followed by the choice of the one with the highest degree of preference. The decision process operates on routes contained in the ADJ RIBS-IN and is responsible for selection of routes to be used locally by the speaker, selection of routes to be advertised to other BGP peers, route aggregation, and route information reduction. The decision process takes place in 3 distinct phases, each triggered by a different event. Phase 1 is responsible for calculating the degree of preference for each route received from a peer. Phase 2 is invoked on completion of Phase 1. It is responsible for choosing the best route of all those available for each distinct destination and for installing each chosen route into the LOCRIB. Phase 3 is invoked after the LOCRIB has been modified. It is responsible for disseminating routes in the LOCRIB to each peer according to the policies contained in the PIB, and the PIB, I forget what that stands for. Is it information base? Let's look it up. Policy information base. Route aggregation. Oh, I forget which one I read. Let's read Phase 2 again. Phase 2 is invoked on completion of Phase 1. It is responsible for choosing the best route of all those available for each distinct destination and for installing each chosen route into the local RIB, which is routing information base. Phase 3 is invoked after the local routing information base has been modified. It is responsible for disseminating routes in the local RIB to each peer according to the policies contained in the policy information base. Route aggregation and information reduction can optionally be performed within this phase. Phase 1, calculation of degree of preference. The Phase 1 decision function is invoked whenever the local BGP speaker receives from a peer an update message that advertises a new route, replacement route, or withdrawn routes. This kind of looked a little misspelled. I guess the S kind of looked strange to me, so I just wanted to make sure I wasn't going nuts. The Phase 1 decision function is a separate process, comma F, which completes when it has no further work to do. The Phase 1 decision function locks an ADJ-RIB-IN prior to operating on any route contained within it, and locks it after operating on all new or unfeasible routes contained within it. For each newly received or replacement feasible route, the local BGP speaker determines a degree of preference as follows. If the route is learned from an internal peer, either the value of the local pref attribute is taken as the degree of preference, or the local system computes the degree of preference of that route based on pre-configured policy information. Note that the latter may result in formation of persistent routing loops. That does not sound good. If the route is learned from an external peer, then the local BGP speaker computes the degree of preference based on pre-configured policy information. If the return value indicates the route is ineligible, the route may not serve as an input to the next phase of route selection. Otherwise, the return value must be used as the local pref value in any IBGP re-advertisement. The exact nature of this policy information and the computation involved is a local matter. Phase 2, route selection. The Phase 2 decision function is invoked on completion of Phase 1. The Phase 2 function is a separate process which completes when it has no further work to do. The Phase 2 process considers all routes that are eligible in the ADJRIBS-IN. The Phase 2 decision function is blocked from running while the Phase 3 decision function is in process. The Phase 2 function locks all ADJRIBS-IN prior to commencing its function and unlocks them on completion. If the next hop attribute of a BGP route depicts an address that is not resolvable, or if it would become unresolvable if the route was installed in the routing table, the BGP route must be excluded from the Phase 2 decision function. If the AS path attribute of a BGP route contains an AS loop, the BGP route should be excluded from the Phase 2 decision function. AS loop detection is done by scanning the full AS path as specified in the AS path attribute and checking that the autonomous system number of the local system does not appear in the AS path. Operations of a BGP speaker that is configured to accept routes with its own autonomous system number in the AS path are outside the scope of this document. It is critical that BGP speakers within an AS do not make conflicting decisions regarding route selection that would cause forwarding loops to occur. For each set of destinations for which a feasible route exists in the ADJRIBS-IN, the local speaker identifies the route that has A, the highest degree of preference of any route to the same set of destinations, or B, is the only route to that destination, or C, is selected as a result of the Phase 2 tie-breaking rules specified in section 9.1.2.2. So this is we love oranges because oranges mean pure refreshments, weight, origin, or weight, local preference, origin, and then like B is like I don't even know, but that, and then that's just for the Cisco implementation of that. So this is the kind of stuff yeah. So it goes by local preference. Then if it's the only route, then it'll go from that. But the tie-breaking process is something that will be covered in section 9.1.2.2. The local speaker shall then install that route in the local routing information base, replacing any route to the same destination that is currently being held in the locrib. When the new BGP route is installed in the routing table, care must be taken to ensure that existing routes to the same destination that are now considered invalid are removed from the routing table. Whether the new BGP route replaces an existing non-BGP route in the routing table depends on the policy configured on the BGP speaker. The local speaker must determine the immediate next hop address from the next hop attribute of the selected route. See section 5.1.3. If either the immediate next hop or the IGP cost to the next hop, where the next hop is resolved through an IGP route, changes, Phase 2 route selection must be performed again. Notice that even though BGP routes do not have to be installed in the routing table with the immediate next hops, Implementations must take care that before any packets are forwarded along a BGP route, its associated next hop address is resolved to the immediate directly connected next hop address, and that this address or multiple addresses is finally used for actual packet forwarding. Unresolvable routes shall be removed from the locrib and the routing table. However, corresponding unresolvable routes should be kept in the ADJ RABS-IN in case they become resolvable. Route resolvability condition. As indicated in section 9.1.2, BGP speakers should exclude unresolvable routes from the Phase 2 decision. This ensures that only valid routes are installed in the locrib and the routing table. Route resolvability condition is defined as follows. Number 1, a route RTE1 referencing only the intermediate network address is considered resolvable if the routing table contains at least one resolvable route, for instance RTE2, that matches RTE1's immediate network address and is not recursively resolved directly or indirectly through RTE1. If multiple matching routes are available, only the longest matching route should be considered, as is the case with any routing decision. The longest matching route is what is taken, and I think you can change that through metrics, administrative distance, what have you. But if there are multiple choices, it will choose the longest match. Number 2, routes referencing interfaces with or without intermediate addresses are considered resolvable if the state of the reference interface is up and if IP processing is enabled on this interface. BGP routes do not refer to interfaces, but can be resolved through the routes in the routing table that can be of both types, those that specify interfaces or those that do not. IGP routes and routes to directly connected networks are expected to specify the outbound interface. Static routes can specify the outbound interface, the intermediate address, or both. Note that a BGP route is considered unresolvable in a situation where the BGP speaker's routing table contains no route matching the BGP route's next hop. Mutually recursive routes resolving each other or themselves, also fail the resolvability check. It is also important that implementations do not consider feasible routes that would become unresolvable if they were installed in the routing table, even if their next hops are resolvable using the current contents of the routing table. An example of such routes would be mutually recursive routes. This check ensures that a BGP speaker does not install routes in the routing table that will be removed and not used by the speaker. Therefore, in addition to local routing table stability, this check also improves behavior of the protocol in the network. Wherever a BGP speaker identifies a route that fails the resolvability check because of mutual recursion, an error message should be logged. So it looks like they're outlining a difference here between BGP and IGP. So IGP routes and routes to directly connected interfaces are expected to specify the outbound interface. Static routes can do either, but BGP routes do not refer to the interfaces, but can be resolved through the routes in the routing table that can be of both types, those that specify interfaces and those that do not. So I guess after reading that, I just want to take a quick look here into my lab, and I want to see what kind of with new eyes after reading this, what the difference between a route learned by OSPF looks like and what one learned by BGP looks like. So let's do a little bit of labbing here. And this should be pretty easy, I'm hoping. I'll use Junipers for this. So yeah, let's just do a brand new project called Untitled. And then we're going to use Junipers. It's probably my strongest device because that's the one I took the IE on, even though I only got 17 points on it. That is pretty darn, like, the way I see it is like, hey, you know, if you score a basket in the NBA, you retire and you've only gotten 2 points. You scored 2 points in the NBA. Like, that's a big deal. That's the way I kind of look at it that way. Oh, my vacuum cleaner failed to start because I haven't emptied the dustbin. Oh my god. Well, anyway, these will be up very shortly now that I changed this over to Ubuntu. I'm already able to open a console on it. Yep, and it's already booting up. So let's just keep reading while that's up, but then we'll go back and we'll look at with new eyes after reading the difference between a route learned from OSPF and a route learned from BGP. But in the meantime, this is section 9122, breaking ties, phase 2. And actually, I will be back in just a moment. In its ADJ RIBSIN, a BGP speaker may have several routes to the same destination that have the same degree of preference. The local speaker can select only one of these routes for inclusion in the associated LOC RIB. The local speaker considers all routes with the same degrees of preference, both those received from internal peers and those received from external peers. The following tie-breaking procedure assumes that for each candidate route, all the BGP speakers within an autonomous system can ascertain the cost of a path, interior distance, to the address depicted by the next hop attribute of the route, and follow the same route selection algorithm. The tie-breaking algorithm begins by considering all equally preferable routes to the same destination, and then selects routes to be removed from consideration. The algorithm determines as soon as only one route The algorithm terminates as soon as only one route remains in consideration. The criteria must be applied in the order specified. Sorry, I like to Purell my feed every once in a while. Several of the criteria are described using pseudocode. Note that the pseudocode shown was chosen for clarity, not efficiency. It is not intended to specify any particular implementation. BGP implementations may use any algorithm that produces the same results as those described here. So they're fake algorithm that may or may not be the most efficient way, probably won't be the most efficient way, is listed here in multiple parts. First part, part A, remove from consideration all routes that are not tied for having the smallest number of AS numbers present in their AS path attributes. Note that when counting this number, an AS set counts as 1, no matter how many AS's are in the set. So the AS path attribute, the first consideration when there's a tie is which route has the shortest AS path attribute. But if there's multiple routes with the same length of AS path attributes, including a route that has a set of attributes all together as an AS set, but the same number, and that counts as a single attribute. So you can have one route with 7 attributes and run one route with 6 attributes. But if the route with 7 attributes have 6 of them, have all 7 of them, have 2 of them in a set, you've got a set of 2, and then you've got 6 attributes, and then you've got 5 attributes. So 5, 6, 7, but you've got a set of 2, so it just counts as 6 altogether. So they would still be a tie in that case. All right, so if there's a tie still, because you've got multiple routes that have the same length of AS path attribute, the same number of AS paths, or the same number of AS paths and AS sets, then it goes to the next tiebreaker criteria, criteria B. Remove from consideration all routes that are not tied for having the lowest origin number in their origin attribute. Okay, so it's starting to get interesting here. So let's make sure we got those routes so we can actually see on the device how things are looking. Okay, we'll go with internal. Oh, we gotta have a group. Yeah, my keyboard, I have a new keyboard I'm thinking of purchasing, but I gotta push the keys 2 or 3 times just for them to actually work, and I've gotta type them in a certain way. And oh, I forgot to say, okay. Because I named the group internal, I thought I already did the type internal command. There we go. Yeah, this keyboard just doesn't work anymore. Alright. Oh, and I got the wrong neighbor. God damn it. There we go. It's amateur hour here, I guess. Alright, time for the other router. Alright, so we should be able to ping now. That's the first step if you want to set up BGP, because it rides on that TCP connection. So if you can't ping across from your neighbor addresses, you're certainly not going to have any luck. But now that we've got that, let's see if our neighborship came up. Alright, so the neighborship is up. So the next step, we're going to be actually distributing some routes over so that they are learned on router 1. So let's set up a loopback address. And we'll do the route 9.9/32, and then we'll do edit policy options, policy statements, send routes, and we'll do set term LO0 from route filter 9.9.9.9/32 exact, and we're going to say then accept. All right, so now we're going to apply that policy. Here we go. So, and then it's not going to get a next hop if we do this, so it might show up as a hidden route. But let's just see what we get, and if I've got to update the next hop on it, I will do that. So one thing we can do before going into this next device, which I will do, I've got router 2 back open here, is make sure that we're actually sending the route. We're going to show route advertising protocol BGP, and then the neighbor we're sending it to, which is that one for router 1. And here you go. We can see we are sending a route. It's going to be next hop self. I think that happens automatically if it's an iBGP route. But you know what? I don't know for sure, so let's switch it over to an eBGP route and see what happens. So to do that, all we need to do is change the local AS and then change the type from internal to external. So we'll start on router 1. And we'll change this from internal to external. Okay, and then we'll change the local AS to, we'll leave it at 1, we'll change it on the other side just so it makes a little bit more sense. Oh, you have to give it the external peer though. Okay, so it's going to be, the group is going to be named kind of tricky, it's going to have the wrong name, but that's okay, we'll just go with it for now. This will be temporary, I'll roll back all these changes eventually. What I will do is I'm going to make sure I have this output here to compare, so I'll put that in a notepad so I don't lose it. Alright, and then I will finish changing this by deleting the designation as internal and set it to external. And just a reminder, this is just the name of the group, so this doesn't actually make it internal or external. The type command does that, but we do need to specify the peer AS now. So we got one more step. All right, and that should do it. Actually, there was a third step that I missed. I've got to change my local AS here to AS2, because that's what I decided to use on the other side. And I could have gotten a clue there, because if you have an external type, you'll never have a local AS that matches your peer AS, and that is what I had, so that is certainly not going to work. Alright, so let me rerun that command to show this one here. And let's see what looks different about this output. Oh, so big difference. Okay, that's just because it took time for that to flap. Alright, so I don't see any difference at all, even though it's learned through eBGP instead of iBGP. We still have a next hop of self. We still have, actually there is a difference. We don't have a local preference now. Okay, so I was thinking, what I thought this would look like is I thought we would still have a local preference, and then I didn't think we'd have a next stop hop. So this is what I was expecting to see here, but instead this is what showed up. No local preference, but still a next hop of self. So one thing I definitely need to do going forward is just understand BGP next hops a little bit better. I think there's definitely problems and gaps in my knowledge with that. So with that being said, let's continue on with the RFC. Hopefully I can learn that better from that. Let's just say that I might have lied here. We're going to do one more thing. We're going to we're going to put an OSPF route side by side with a BGP route and see the difference. So set protocols OSPF, area 0, interface G00.0. There we go. And then LO 0.0. Okay, so I might have to do more than this. Yeah, so I've got to do more than this. And there's a reason for that. And I think the reason... I'm actually surprised by this, because I thought... oh, you know what? Maybe it's 190s. So let's try this. We're going to come back to the candidate configuration, and we'll do a show pipe display set, pipe no more, and now we're going to deactivate the BGP config. So we'll lose that neighbor, and we'll take a look at what the routing table looks like now. What the hell? Okay, that's confusing. So the reason I'm confused by that is because we've got a administrative distance here of 10 now. Now we're learning it through OSPF since we don't have that BGP neighbor. So I'm just really surprised that the higher administrative distance route took over, took precedence over this lower one here. So let's see what happens if I add it back. So I'm thinking what happened is the routing table never updated. I think yeah. Well, this is interesting. Now we've got it back in, but now we've got both of them. We've got BGP as a backup route. Okay, let's see what happens if I deactivate the OSPF now. Okay, so now we get this, just as we had it before. So what if I activate OSPF now? Okay, same deal. So let's see if maybe I just needed to sit on it a little bit and it would take over, but we can see for some reason OSPF isn't taking over for BGP, even though it's got, oh, okay, it just takes a while. Okay, it is, okay, that's what I was expecting. I just didn't think it would take that long. Let's take a look at what's actually happening on the wire with that, because that's actually pretty interesting that it takes that long. I'm wondering if there's like a hold timer that's expiring. I mean, we'll see it. We'll definitely see everything here. So so where it gets tricky is let's go back here. We're going to do configure private. We're going to do rollback 1, show pipe compare. So we're going to deactivate OSPF. And now we're going to see we just have that BGP route. Now what we're going to do is reactivate OSPF, but we're going to see a delay where for a number of seconds we still have the BGP route in there, even though it is a higher distance and duplicate entries to prefixes. Here for prefix 9.9.9.9/32 are only shown as active for the entry with the lowest distance. And if they have a tied distance, you can have an equal cost path that load balances amongst it. But in this case, we don't have that. OSPF usually has a higher, a lower administrative distance than BGP. All right, so let's roll back that last configuration. Okay, and we'll see it take a little bit of time, but now we're going to see here what is going on. There we go, and it's back. So let's stop the capture. There we go, and we can see the reason it wasn't on there is because it had to go through this whole process here. Once it started exchanging hello packets, it had to, we could follow the, let's do a, yeah, follow, oh, I can't follow that? Oh, it's a multicast. Prepare as, oh, I want to do a conversation filter, IPv4. All right, there we go. Anyway, I gotta take a quick break. I'll be right back soon. All right, I'm back. You can see the reason it took so long for it to show up is we had this exchange. Let's apply a filter here, so we're only seeing it from one side. So we're gonna go here. We're gonna choose what we want to filter for. We want to filter for the source IP address. So we're going to do apply as a filter, and we want to do and selected. There we go, and now we've got this as the source IP address. So we see this sends a database description packet, and let's look at the OSPF down here. Yep. So there we go. So it's got a, oh, why is it? Oh, because I have that selected. Okay, there we go. Now this is selected. Perfect. Okay, so we've got our database description. Gets sent out. So, and then we send out a type 1 LSA, and then link state request, and link state acknowledge. So this is something I hope to dive into deeper too as part of this Wild Networking series, going through the RFC for OSPF. I want to read a lot more RFCs, look at wire captures, ladding. So interesting things to come soon. We see that we do have a next an interface listed here, even though in the RFC it said that it's not something that will that is gonna be there for BGP routes. I guess I forget exactly what it said. I don't want to lose my place here, so I'll highlight that and I'll go back and try to find this. Yeah, so BGP routes do not refer to interfaces, but can be resolved through the routes in the running table that can be of both types. Those that specify interfaces or those that do not. So even though a BGP route does not refer to an interface, and we can see that is true, and just we know from what we've learned so far that is true. BGP routes are based on TCP, and it's just TCP data. It doesn't actually refer to any interface or anything like that. It doesn't know anything about actual like links on the network the same way that OSPF does. You can see in OSPF we will have so we've got like a link state ID. So we've actually got things referring to links here, but we don't have anything like that in BGP. So let's look at OSPF and see everything we've got that talks about links, and we'll see some of it because it's a link state protocol. It keeps a map of the network. So here's the OSPF database description. Look at this. We've even got a MTU for the interface. yeah, so okay, so already we've seen two pieces of information that specifically refer to actual interfaces on the router. And I'm hoping to see more of that. So these are all similar. Let's see if there's anything in a link state request. So here we're actually requesting information about links. So we got link state ID. Yeah, so we're asking about both the loopback link and the GE000 link. Yep, and then we're providing back information, the information that was requested. Yep, so here's the link data. We've got the ID, subnet mask. We've got a link type. So links. We're talking about links. But BGP, we're not talking about links at all. We've got nothing in here about links. These are the updates. So let's make the traffic a bit more interesting. We're gonna open a new capture. Okay, and then we're going to flop the config. Okay, so it looks like the capture. Let's do start Wireshark. There you go. Alright, and then we will roll back and commit, and that'll give us some more interesting traffic to look at. But even with things getting tricky, we see a three-way handshake, we see open messages, and then we see keep alive messages, and we'll even see an update message to, right here, to exchange that loopback address. But we don't have any information at all about the fact that about what kind of, about links. We don't see anything in here referring to a link. We have network layer reachability information, we have prefix length, but it's referring to it as data, not anything at all relating to a specific device or a specific port or anything like that. And that's quite a bit different than other protocols, IGPs, such as OSPF. Okay, so I lost my, okay, so C is the next part too. I might be ending this at phase 3, but let's continue on. C, remove from consideration routes with less preferred multi-exit discriminator attributes. Multi-exit discriminator is only comparable between routes learned from the same neighboring AS. The neighbor AS is determined from the AS path attribute. Routes that do not have the multi-exit discriminator attribute are considered to have the lowest possible multi-exit discriminator value. This is also described in the following procedure. For n equals all routes still under consideration. For n equals all routes still under consideration. If the neighbor AS of all routes under consideration equals the neighbor AS of all routes still under consideration, and the MED value is less than this particular route being considered than the other routes, then remove route M from consideration. So it goes with the highest value of MED, and we can see routes that don't have it at all are considered to have the lowest possible. In the pseudocode above, MEDN is a function that returns the value of the route n's multi-exit discriminator attribute. If route n has no multi-exit discriminator attribute, the function returns the lowest possible multi-exit discriminator value, for example, 0. Similarly, neighbor ASN is a function that returns the neighbor AS from which the route was received. If the route is learned via iBGP and the other iBGP speaker didn't originate the route, it is the neighbor AS from which the other iBGP speaker learned the route. If the route is learned via iBGP and the other iBGP speaker either A, originated the route, or B, created the route by aggregation and the AS path attribute of the aggregate route is either empty or begins with an AS set, it is the local AS. If a multi-exit discriminator attribute is removed before re-advertising a route into iBGP, then comparison based on the received eBGP multi-exit discriminator attribute may still be performed. If an implementation chooses to remove multi-exit discriminator, then the optional comparison on multi-exit discriminator, if performed, must be performed only among eBGP learned routes. The best eBGP learned route may then be compared with the iBGP learned routes after the removal of the multi-exit discriminator attribute. If multi-exit discriminator is removed from a subset of eBGP learned routes, and the selected best eBGP learned route will not have multi-exit discriminator removed, then the multi-exit discriminator must be used in the comparison with the iBGP learned routes. For iBGP learned routes, the multi-exit discriminator must be used in route comparisons that reach this step in the decision process, including the multi-exit discriminator of an eBGP learned route in the comparison with an iBGP learned route, then removing the multi-exit discriminator attribute and advertising the route has been proven to cause route loops. Okay, so let's use another link here, G001, to learn about the multi-exit discriminator a little bit better. Okay, so we're going to set interface family inet address 1/3 commit. Alright. Perfect. Okay, so we should have multiple exits now. All right, but I'll deactivate. Oh, actually, I'm going to need to set up another neighbor in order to have multiple exits. Okay, so I've got multiple exits now. So this should show up once I've got that coming up, which I should pretty soon here. There we go. So now I've got multiple exits. So now we can discriminate between the multiple exits by sending a discriminator value along with our advertised routes. So on this side, we don't have any advertised routes. Yep, we don't have anything. We're advertising the routes from this side. So this is where we configure a multi-exit discriminator. Because a multi-exit discriminator is a path attribute, you send it to another route, and then the route uses that to send routes to you along a preferred link. Alright, so I think I forget how to do this. It's tricky. Like, they don't use MED, of course. Why would they? That would be easy. Okay, yeah, I think you add it here, and it's called something like really weird. It's not called metric, I think. That would be too easy. It's not called preference. That would be too easy as well. I think it's actually then. Huh. Okay, so let's try this. This is one of my favorite things to do. We're going to do run, help, or let's do a top, exit, help, apropos, pipe match, help, pipe match, MED. Here we go. So now we've got help topic on MED metric. Ah, here it is, metric out. And you put that just in the group. Actually, do you put it in the group or do you put it under a neighbor? So you can do it for a community, you can do it for a neighbor. Let's do it for a neighbor. Okay, so now we can choose which neighbor we want to have the metric out. So let's configure it on both of them. So here we're going to set a metric out of 10. Okay, and then on our second neighbor, we're going to do a metric out of 11. Alright, so now when we look at this, we're going to have much different results. We've only got a single one, the one with the oh, actually it goes with the, what the hell? Oh, you know what? It's because we've got the active OSPF route. That's the one it picks. It just shows you the other two. It doesn't have to make a decision about which one to make active since it goes with the OSPF route. So we'll deactivate the OSPF route. Okay, and now we'll see the one with the higher MED value. Okay, well actually I was wrong. It's the one with the lower MED value that gets chosen. I thought it was higher, but we can see clearly it is the one with the lower. Alright, so let's continue on. If a multi-exit disk attribute is removed before re-advertising a route into iBGP, then comparison based on the received eBGP multi-exit discriminator attribute may still be performed. If an implementation chooses to remove multi-exit discriminator, then the optional comparison on multi-exit disk, if performed, must be performed only among eBGP learned routes. The best eBGP learned route may then be compared with iBGP learned routes. After the removal of the multi-exit disk attribute, if multi-exit disk is removed from a subset of eBGP learned routes and the selected best eBGP learned route will not have multi-exit disk removed, then the multi-exit disk must be used in the comparison of the iBGP learned routes. For iBGP learned routes, the multi-exit disk must be used in route comparisons that reach this step in the decision process, including the multi-exit disk of an eBGP learned route in the comparison with an iBGP learned route. Then, removing the multi-exit disk attribute and re-advertising the route has been proven to cause routing loops. D. If at least one of the candidate routes was received via eBGP, remove from consideration all routes that were received via iBGP. E. Remove from consideration any routes with less preferred interior cost. The interior cost of a route is determined by calculating the metric to the next hop for the route using the routing table. If the next hop attribute for a route is reachable but no cost can be determined, then this step should be skipped. Equivalently, consider all routes to have equal costs. This is also described in the following procedure. For n equals all routes still under consideration, for n equals all routes still under consideration, if the cost of n is lower than the cost of m, remove m from consideration. In the pseudocode above, cost n is a function that returns the cost of the path interior distance to the address given in the next hop attribute of the route. Remove from consideration all routes other than the route that was advertised by the BGP speaker with the lowest BGP identifier value, that's F. And the final one, G, prefer the route received from the lowest peer address. Alright, so I think that's going to be it. The last thing I do, though, is I want to prove that the lower MED value is the favored one. So I'm going to put this metric out down to 9, and we'll see out .11 is going to be preferred. Kind of unnecessary, but it's just something I want to do. Alright, and we can see instantly it skipped up because the metric is 9 and the lower metric is the one that's preferred. Alright, that's going to be it for this video. In the next one, we'll be reading about route dissemination.